normal in this case. So long short-term memory is an artificial recurrent neural network architecture used in the field of deep learning. LSTM networks are a type of RNN. Okay, LSTM networks are well suited to classifying, processing, and making prediction based on time series data. If you don't have time series data, if you have an image data, then you can go for CNN also. LSTM networks have some internal contextual state cells that act as long-term or short-term memory cells. What it means, let's see from this example. Consider that we want to predict the next number of the following sequence 8, 9, 10, and then what will be a next. So by saying we can say that next will be 11. Now in this case, however, if you provide the sequence 6, 8, 10, again the last state is 10, last value is 10, but in this case next output will be 12. So what LSTM does, it use the contextual information, means previous information, and based on that it predict the output. In this case what it will predict? 11, and in this case it will predict 12 value. Okay, so like this LSTM works. So if you have sequential data, use LSTM for that. See, this data I have, actually the example which I am taking, that is a from PhysioNet 2017 challenge. They use the deep learning and signal processing, both they use to create this model. So there is one, if you are working on ECG, you will be aware of that what is AFib, that is atrial fibrillation. It is a type of irregular heartbeat that occurs when the heart's upper chambers, that is the atria, beat out of the coordination with the lower chambers. It is, and lower chambers is called ventricles. Okay, so this is a normal ECG signal, and this is a infected one, abnormal, that is atrial fibrillation. Okay, so this kind of data we have, which we are going to train it. And you see, just yesterday I trained it, and here you see how much time it took. 120 minutes, means 2 hours it took to create a deep learning model because of big data. Okay, now I am going to switch here in MATLAB. Let me show you how it work actually. So data which I have, data is like this. So here it is. Just wait a minute, let me show you the data which I have here. So these are the data which I have. Fine. These are the raw data of ECG signals. Okay. Let's start step by step how to train this model. So I am using a live script for that again. In live script you can visualize your output as well. I downloaded that data. Let me clear any variables. It is already clear. So I am going to load that data. I have that data as a .mat file. Okay. And second thing, I have, when I load this data, when I switch here, I will have two kind of data: signals in a cell and labels. You see here in a cell, how many samples do we have? 5788 samples are available in a cell, and for each sample we have class normal or abnormal as a category. So like this you have to prepare your data. Time series data write in a cell, and labels will be your as a category. Okay, after reading this, just from here what I am going to do, from the cell 1 to 5 index, I am just reading that data. So here you can see these are the samples. First sample is of 1 into 9000, means first sample which we have. In the first sample again there are 9000 samples. So like we have different size of array here for ECG signals as a cell here, and these labels for each samples are normal, 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 and abnormal. And in the summary if I give, so it is showing you that the normal data are 5550, and abnormal samples we have 738. So always remember, during training we have to equalize this, so we'll get the better accuracy. Otherwise what it will do, it will train all data as a normal, so we have to equalize this as well. Okay, now the good thing, if you are using MATLAB, and if you have data in cell and you want to apply any function on a cell, so what will you do? Maybe you are going for the for loop and you are calling each index from the cell and you are applying your algorithm, but that is not a good way. You can use cellfun for that, cellfun, and here using @ function handle you can apply this function on cell. This is my cell signals, so this is your function. You can design your function and you can call using @. What it will do, it will be applied on all index, means all samples which are available in a cell. So in this case what function I am applying? To find out the length of it, and further we are plotting this length as a histogram to count that samples, that what kind of samples are available there. So here you see on x-axis we have length and on x-axis we have count. So if I click on this, so here it is showing that between 90,000, sorry 9,000 to 9,050 there are 4,234 samples in this range. This is the histogram which is showing. Fine. Next what I am going to do, I am going to extracting first sample from here and second sample from abnormal. First from normal and second is abnormal, which is index number 4, and both I am plotting it here. So is it very simple? You can use subplot to plot in the same figure window as a sub figure. So the first which you see, that is normal. So you can see difference here in this wave. So this normal waves is going like zigzag, but in abnormal you can see we are getting some spikes here, right? Now we are going to prepare the data. So first we are going to segment these samples, like as in the summary what we saw, that all samples were not equal. Some has size of 9,000, some has size of 18,000. So using these signals, what we are doing, we are equalizing all samples. We are making it as equal around 9,000. Okay. Now what we are doing here in next step, we are extracting abnormal inputs samples. If I give this command, it will give me the index wherever this level is equal to A. I will get the logical index as a 1 0, and I am extracting that signals which is abnormal. Same I am extracting the labels as well which are abnormal. Same we are doing for the normal as well. Why we are doing this? To equalize this. As I told that abnormals were lesser than normal data, right? So we have to make it equal. To make it equal, further we are using the random distribution here. So maybe in your case you don't have to do this kind of pre-processings. After creating some data, what we are doing it, we are using concatenating all data like this. So here's the reapmat. Reapmat is used to repeat the matrix. Let's say that I have a 2 into 2 matrix. If I am using reapmat and matrix name and comma 2, so what it will do, to double, it will become a double. First matrix, then it will be replica of second in a single matrix. So it will become a 4 into 4 matrix. It will become 4 into 2 matrix. So same after equalizing this, we are just concatenating training data and testing data. This is the input, this is the output for training, and here this is the input for testing, and this is the output for testing. Now if I click on summary, it will show me that how many samples are there. Now you see for training total samples are 4,438, and in abnormal and normal also. Now they are equalized. So what we have to do, let's say if you have less data, just copy it, concrete it and make it equal. This is the step which I did here. Next we are going to define the layer. So these are the layers here actually. Sequential input layer. Input is one only, that is normal or abnormal. So one input at a time it is coming. And this is a bi-LSTM layer. So it work in the bi-directional. Okay, fully connected layer. Here we provide number of objects. So in our case, number of objects is means number of classes. Number of classes we have normal and abnormal. So two. Softmax layer, what it does, it detect the probability. After fully connected layer, it will extract the probability. Let's say that abnormal probability is higher than normal. So what it will do, it will classify as a normal. If probability of abnormal is higher than normal, then output will be abnormal. So what classification layer does, it classify based on the probability. Okay, after defining this layer, now we are providing here options, training options. So here we are using adaptive movement estimation algorithm. Just wait a minute. Fine. Maximum epochs is 10, means it will run 10 full cycle. Right now if I run it, it will take 2 hours, so I am not going to run it. Already I saved that model. Minimum batch size. If you have big data, you can define the batch size. At a time, 150 samples will be trained. And one batch size is called one iteration. Now this is the initial learning rate. You can increase or decrease it. If you decrease it, your initial learning rate, your accuracy will be high. But you have to be careful, it can be a overfitting also. Like as a human, if you read anything slowly, we remember for a long time. So when you reduce the initial learning, your accuracy will increase. So same it happens here as well. Same as what will be a sequence of length, means at a time from every samples how many arrays will come, and further execution environment is auto. Okay, execution environment is auto means if I have a GPU supported, then my model will run on GPU, otherwise it will run on CPU. I want to see the plotting progress also, so I can run, define this value also, and this will be a progress when I run this. So first is accuracy and second is losses. So while training using raw data, the accuracy was around 60% and the losses were around 0.6 somewhere. Okay. Now here to train this data, just we use the inbuilt function in MATLAB, train network. This is the training data as the input and this is Y-train output, and this is the layers which we defined it, and here is the option file, option which we defined it here. So all this we defined it. Now we have to click the train. So I am not going to train, just directly I am going to load that model. So model is trained as a net here. If I type here net, this is the model. Total 5 layers are available there. Okay. Further classification. So what we are doing, we are classifying on what? On training data, X-train. Means already we created a model, then again we are taking that input to classify it. Fine. Okay, and the sequential length is 1000. So if I run this, it will classify it, and further to find out the accuracy like we did in a machine learning, if predicted value is equal to this trained value. I think someone got access of my machine. I can check the name. Okay, so don't please open this team viewer. So here when training predicted value is equal to training value, I will get value 1, and when I do a sum of it, I will get the total correct predicted value and divide by total number of training samples. And further we are plotting the confusion matrix of it also. So you see here total accuracies it is showing 62.97 in this case. Let's check for the testing data as well. So when I run this, it will classify on testing data which I had here, and for the same thing we are doing it, original output and predicted output, sum of it and divide by total number of samples into 100. In this case also 60% accuracy is coming. To enhance this accuracy further, what here you can see this confusion matrix which were abnormal, 350 were perfectly classified and 208 were 208 were misclassified. So 60% were perfectly classified as a abnormal and 39 misclassified. Same if I go for the normal, 61% were perfectly classified and 38 misclassified as a abnormal. Fine. So another way what we can do, improve the performance with feature extraction. We can extract the features. First feature what can be extraneous frequency. Like let me plot the spectrogram of this one ECG signal first of all. Then I will explain that what is this. To plot the spectrogram of your time series data, we use this function FSP spectrum. Okay. So it will give me a spectrogram of it. So of normal and abnormal. What is this graph actually? So on x-axis it is time, on y-axis it is frequency. So what it is showing you, with respect to time, if any frequencies are introduced there or not. And based on the color, blue if somewhere is there, then it means there is no frequency, zero frequency. When you go up, it is showing you higher frequency. So what we can do, what features we can extract from there, that at every time what frequencies were introduced, that is an instantaneous frequency. And we'll use that as a feature to train our deep learning model again. So, and another is spectral entropy. Spectral entropy, you know Shannon entropy concept, right? That is the entropy. I think when you will have one course that is IIT, so you know that what is a spectral entropy. So these features you can use in machine learning also. So in this case, I am going to use deep learning. So what I am going to do, whatever ECG signals raw data I have, I am going to extract the instantaneous features from that and spectral entropy from that. Okay, the function is pentropy to extract the entropy from them. So these two features we will train it. So let me extract from one normal and one abnormal. If I extract that instantaneous frequency, then how it looks like. So this is the, so here you see on y-axis is frequency and on x-axis is time. So with respect to time, how many frequencies were generated during ECG signal. This is the graph. This data we are going to use for training this time. So here is the again CellFun, and this is my function which I am going to apply on every index of the function. And uniform output false. What it will do, this function, what it will do, if you don't have the same size of data in your CellFun, then you can give this command. So output will be saved as a cell again here. Okay, this function we are applying on every index of cells using this. So for the training and for the testing both. I am loading that. I am not going to run. Actually, it will take long time. Now if I okay, it is still running. Now if I plot that entropy, it will look like this. Okay, so this is the entropy of, that is a spectral entropy of normal signal, and this is of abnormal signal entropy. Okay, we applied on single data. Now using CellFun, we are going to apply on all data. Fine. After applying this, if I run this, two samples we had, instantaneous frequency and entropy. So you see two rows created, 2 rows into 255. So right now we have two features in every cell index. Okay. Now we are creating data for training and testing here. Okay, so what we are doing in this case, as I told, if you have data, let's say 1000 or 2000, something like that. So what we can do, if you have a big data like this, means that the value is big, what you can do, you can minus the mean value from that. You can normalize your data for better efficiency, or you can, what you can do, you can normalize your data between 0 to 1. So same thing here we are doing it. We are taking the mean value, then further we are minusing that mean value from that, from all data which I have as a cell. So again we are using the cell fun, and the function is what, x minus mean value. So from every value it will be minus from there. Okay. So after doing this, this is the mean value which is showing you, that is minus. This is for instantaneous frequency, and this is for the entropy. Now further design the layer same way. So previously we had only one input, now we have two features. So in sequence input layer we will have two inputs, as value will be 2, and 100 in by LSTM layer, 100 is showing number of neurons. Fully connected layer, again number of objects we have 2. Softmax layer will be used to create the probability, and classification layer will classify based on this probability. Okay. And further, this option files, maximum epochs, minimum batch size, initial learning rate. I ran this model also, and the progress, training progress, you can see it here, the second one. So you see in this case, while training it took only 11 minutes. Before I use raw data, it took 2 hours, and after extracting the features, just it took 11 minutes to train it. And now further you see in this graph, the accuracy is increased, that is more than 80%. When we did some pre-processing on that data, after extracting the instantaneous frequency and the entropy, the accuracy is increased, and the losses are also decreased. You can see it is below 0.5 in this case. Okay, so I am again not going to train this. Already I loaded data, that model. If I train, it will take again 11 minutes. Okay, so here this is my model. Further, you can classify on test data to find out the accuracy. So we use classify command, and this is my deep learning model, and this is my testing data which I am going to use to classify. Output what we will get, predicted value. Then again we are applying this operator. Whenever this condition will be satisfied, we will get one value, otherwise we will get 0. If I do sum of it, then what it will give me? It will give me the total number of correct predicted values. Divide by total number of samples into 100, it will give me a accuracy. So when I run this, so previous time accuracy was 60%. So let's see that what is the accuracy in this case. So it is still running. So I have a supported GPU, but it is giving warning that in later release this 3.5 CUDA supporting will be removed in future. So it is running on GPU actually. So here you see the accuracy is 86%. So around 26% accuracy is increased. And this is a confusion chart of it. So here you can see the abnormal 413, misclassified 53, and 413 perfectly classified. So 86% from normal, abnormal, classified right means correct, and 11.4 were classified wrong as a normal. In this case, in normal case, 85% classified as a normal, and 15.04 classified as an abnormal. So pink color which you see, it is showing error, blue color is showing that correct classified.